Hi, Assalamualaikum. Today we are going to learn about parametric equations. So what is a parametric equation? So let's consider this plane and the curve C represented by the blue line there. Right, let's say we have the curve C here. We cannot describe the curve C by the function y equal to fx. Why? Because it fails the vertical line test. What is a vertical line test? Alright, so suppose we try to draw the vertical line over that curve. So we note that there are two intersection points there. For the function to be written in terms of y equal to fx, it should pass the vertical line test, meaning to say that it only intersects at only one point for the what do we call vertical line test. Like say for example, suppose we have this graph, right? So we do the vertical line test, right? So anywhere it's only intersect at one point, so it can be written as y equal to fx. Since this curve C cannot be written as y equal to fx, so what should we do? Right, so we can write x and y as functions of time, where time here is actually the parameter. All right, so we can write x equal to ft, which is a function of time, and y equal to gt, which is another function in terms of time. All right, so these two functions are known as parametric equations, and the curve C now is known as the parametric curve. Okay, now let's consider example 1 here. Suppose we need to sketch the curve defined by the parametric equations at equal to t and y equal to t squared plus 1. So what should we do? We can do by finding the values of x and y for different values of t. So suppose we find the value of t equal to -2, so we get x equal to -2 and y equal to 5. If we find for the rest of values of t, we get different values of what we call x and y. So what we try to plot when t equal to -2, all right? When t equal to -2, so we try to plot, we get -2, 5, all right? And so on, -1, 2, 0, 1, 1, 2, and also 2, 5. Right, so we can see that this is a shape like a quadratic parabola curve. So this is actually something like this. But when sketching the curve for the parametric curve, it's important to write the orientation, right? So we know that it starts from from there to that point, right? So that curve is actually from this to this, okay, something like that, right? So it's very important to note the orientation for the parametric curves. All right, alternatively, we can eliminate the parameter from the parametric parametric equations. Suppose we have that x equal to t, so we can rewrite, all right, t equal to x. So we can substitute now t equal to x inside that y, so meaning to say that the variable t is now changed to x, so we get y equal to x squared plus 1. So you already know that when you have the equation y equal to x squared plus 1, it's actually a quadratic curve or parabola, something like this, meaning to say that something like you have the what do we call this is y equal to x squared. Since y equal to x squared plus 1, so it is shifted upwards by 1 unit. All right, so this is the curve. But it's important to write the orientation. So since the orientation can only be determined when we have the different values of t from the previous slide, we have that orientation. All right, so now in the parametric curve, it's important to know what are the initial and terminal points. Suppose we have the parametric equations here, where t is now restricted from a to b only, meaning to say that t starts from a and b ends at b. All right, so we have the initial point where at this point the value of t is actually a. So we have the FA and GA. How do I get this? Meaning to say that when t is equal to a, so you substitute the value of a inside these functions, you have FA and GA. All right, now that is the initial point. So now we go to the terminal point. So the terminal point can be labeled there, where this is just example, right? All right, so this is actually when we substitute the value of t with b, so we have the FB, all right? So it can be any function, so this is like in general form. All right, so you know that it's from the initial point, so we have the orientation from the initial point to the terminal point there. Okay, let's consider the next example. What curve can be represented by these parametric equations? X equal to sine t, y equal to cos t, where t is restricted from 0 to 2 pi. What we can do is we find the value of x and y for different values of t. So t is from 0 to 2 pi. You can start with 0, pi over 2, pi, 3 pi over 2 up to 2 pi. Alright, so let's say we have this table here. Alright, we find the value of x and y for different values of t. So we have this what we call coordinates here. Alright, so we know that when t is equal to 0, it's actually, before I plot that, I just want you to recall this is how I get the values of x and y, right? Like for example, when t is equal to 0, so for the sine will be 0, that's why I got 0 there. For the value of t, which is pi over 2, I get 1 because that's sine. But for cos, when t is equal to 0, so that y equal to 1. And when pi over 2, t equal to pi over 2, then y equal to 0. That's how I get this, right? So you have to, I guess you already memorized this, right? You remember this already, right? It's just that revision for you. Right, so now we know that when we start at t equal to 0, the point is actually 0, 1, where is 0, 1 is that point, right? For next point, which is at t equal to pi over 2, it's actually at 1, 0. Where is the point 1, 0? It's over there. Alright, so we get t pi over 2. Next, we move to when t is equal to pi, which is 0, negative 1 here. Alright, so when 0 negative 1, so we have that point. So next, we have when t equal to 3 pi over 2, we got negative 1, 0. Alright, okay, this one. And finally, we have when t equal to 2 pi, we have 0, 1, which is this point. Alright, so that is 2 pi. So when we try to plot this, actually this it's a circle. Right, it's actually a circle. But what is the orientation? You know that it starts from t equal to 0 here, so it goes to this, goes to this, and finally go back to t equal to 2 pi. That's the orientation. All right, now alternatively, we can eliminate the parameter from the parametric equations. How do I eliminate the parameter here? Alright, so this is the part where you have to recall the trigonometric identity. What if you square both x and y? What happens? Alright, so we will have x squared plus y squared, meaning to say that you will find the sine square t plus y cos square t, right? So you know that from the trigonometric identity, when you find the sine square t plus cos square t, it will be equal to 1, right? No matter what variable it is here, right? With the condition that is actually the same variable. Right, so you get sine square t plus cos square t equal to 1. So you can rewrite this, actually this is equal to 1. So we have x squared plus y squared equal to 1 squared. What does this equation represent? This is actually a circle with the center 0, 0 and radius 1, because the formula for this circle, we have the x minus h squared plus y minus k squared equal to r squared. So this is the center. hk is the center and r is the radius. Right, in this case, the center is actually 0, 0 and radius is 1. So we can draw this, what do we call, a circle for these parametric equations. Okay, let's now move to the next example. Suppose we have to sketch the curve where x equal to cos t, y equal to cos square t. We know that for y, by eliminating parameter, we can write that y equal to cos square of t or cos t square in the bracket, meaning to say that because cos t is actually x, so we have y equal to x square. Right, so we have the y equal to x square. What does this graph represent? This is actually a parabola, right? Which is represent here y equal to x square. It's smiling there. All right, but we have some restriction here. Why? Because we know that cos t, the value is between -1 and 1 only. All right, if you don't believe me, then you can sketch this curve. This is the cos t, right? So this is 1 and -1. So the value is between 1 and -1 and 1 only. So when cos t is between -1 and 1 only, of course cos t is x, so x is between -1 and 1 only. So from this curve, we want just from x equal to -1 and from x until x equal to 1. So that's why we have this curve. All right, so if you try to substitute the value of t with 0, right, so it starts with t. Okay, suppose we have t is 0, so of course x is equal to 1, right? X is equal to 1 cos 0. All right, cos 0 is 1 and y equal to 1. So it starts from 1 1 until -1 1, right? Okay, something like that. Let's move to example 4. We need to find the simplest form of the rectangular equation by eliminating the parameter. So the question asks us to eliminate the parameter. What can we do here? Right, so we have to rewrite the x equal to t minus 1 in this form. All right, so we have t equal to x plus 1. What can we do next? We can substitute the t equal to x plus 1 inside the y equal to t squared minus 3t. So we have this equation now. All right, we substitute the value of t with x plus 1. So of course we have now this. We have to expand it. Right, we expand it. All right, we simplify. After simplifying this, all right, we know that this is actually a quadratic curve. By completing the square, we have y equal to x minus half square minus 9 over 4 square. So what does this mean? All right, so it's actually initially this is the y equal to x square, but since x is now shifted by half unit to the right, all right, so it's something like this, right? It's shifted half unit to the right, but the this value represents that it is shifted downwards by -9 over 4. So it's something like that, right? So it's something like that. So we have this what do we call parabola, right? So if you don't remember this, then go back to those parabola equations, right? Or how you completing the square. What does the completing the square of the quadratic equation means? You need to go back to that. But since in the equation it indicates that t must be greater than or equal to 0, so when you try to substitute the value of t with 0, you get these coordinates when t is 1, when t is 2, and so forth, right? So we have these what do we call points. So you can actually plot, right? You can actually plot this starting from -1 0 until 0 -2 until what do we call 1 -2, all right, 1 -2, somewhere around there. Okay, 1 -2, and then we have 2 0 and 3 4, something like that. All right, so this is actually starting from this initial point to this up to that. All right, in this case we don't have the what do we call the terminal point, right? So this is the direction of the curve. All right, now we want to sketch the curve given by that parametric equations. So what we can do is maybe we can eliminate the parameter. So how to eliminate the parameter? We have to modify this x equal to square root t. So we have t equal to x square because we square both sides of the equation. So when we have t equal to x square, we can substitute the value of the variable t with x square inside this y. So we have that y equal to 1 minus t. So t is substituted with x square, so we have 1 minus x square or -x square plus 1. We know that for the graph which is -x square is something like this. So this is y equal to -x square, but it is shifted upward by 1 unit. So because we add 1 here, so that means we have this graph. Okay, something like that. But right, since in the equation it indicates that t must be greater than or equal to 0, right? T equal to x square, right? So since t equal to x square, when t is greater than or equal to 0, of course x square greater than or equal to 0. So we need to see for that graph just now, right? that something like that. We just need to consider the part where x is start from 0 and so forth. So we have this part only, because we just want the value for the graph when x equal to 0 and so on. All right, so we don't need this part. Okay, something like that. Right, now we're going to review on the tangent of the parametric curve. What is a tangent line? Right, recall that a tangent line is actually a straight line that passes through the curve and touches the curve at only one point. Where is the point? Anywhere. Suppose we want to find the tangent to this curve at this point. So this is actually the straight line that touches the curve at only one point there. Only one point. Next, if I want to find the tangent to this curve at this point, so we have this straight line. Suppose I want that the tangent to this curve at this point, so we have this tangent line there. So now we need to recall that for the tangent line, the slope of the tangent is given by dy over dx. All right, dy over dx. We have the equation dx over dt, which is equal to given by dy over dx over and multiply with dx over dt. If you can see that dx being cancelled, so we have dy over dt. All right, so now we modify this equation. All right, we modify this equation, so we get this dy over dx is actually dy over dt over dx over dt. So this is the gradient of the tangent to the parametric curve, because this is dy over dx, the one that we want. All right, now but with one condition, that the denominator here, which is dx over dt, should not be equal to 0, because if it is equal to 0, then it should be undefined. All right, so now for the horizontal tangent, right, we take the what we call the numerator, which is equal to 0, right? So dy over dt equal to 0. But for the vertical tangent, we take the x over dt equal to 0. All right, now for the second derivative, right, so it's actually given by this formula. So we have this formula, you have to follow this formula. All right, so now again with one condition, that dx over dt should not be equal to 0. Suppose we have example 6 here. All right, we have the curve defined by the parametric equations x equal to c squared and y equal to t cubed minus 3t. We have to find the equations of the tangent to the curve at 3, 0. Right, firstly we need to find the gradient of the tangent. All right, the gradient of the tangent at that point. All right, so we have to find dy over dx. So dy over dx is given by this formula. So do we have dy over dt and dx over dt now? No. So we have to find dx over dt, meaning to say that we differentiate this x, and also we have to find dy over dt. So we differentiate this y, we get dy over dt here, and then only we can substitute inside the formula dy over dx. So we have 3t squared minus 3 over 2t. So now, because we want to find the what we call the gradient of the tangent at point 3, 0 here, right? So please take note that we want to find the value at 3, 0. So we can write t cubed minus 3t equal to 0. How do I get this equation? Right, because we actually have that 3, 0 is actually xy, meaning to say that y is equal to 0. If you substitute the value of y with 0 here, so you have t cubed minus 3t equal to 0. Now we need to simplify this, meaning to say that we have to factorize t. Alright, so we get this 0. So we have t equal to 0. Solving this, we get t equal to 0 and also t equal to plus minus 3. Right, so now we need to substitute the value of t equal to 0, t equal to positive 3, and also t equal to negative 3 inside dy over dx here. But if we substitute the value of t with 0 here, we will get dy over dx being undefined. Therefore t equal to 0 is not considered. All right, because dy over dx will be not defined. Then we only need to consider for the positive root 3, okay, meaning to say that we substitute the value of t with root 3. So we simplify and we get this root 3 is the answer, is the gradient, right? Another one is we have to find dy over dx at t equal to negative root 3. So we substitute the value of t with negative root 3 and we get this value. Now, right, we already obtained the gradient of the tangent. We have to find the equations of the tangent at 3, 0. I just need you to recall what is the tangent. The tangent is a straight line. Therefore, we have the equation of a straight line given by this. Alright, so this is the equation of the straight line. So, for the case 1, we know that the slope at t equal to root 3 is given by root 3. Therefore, we can substitute inside this formula. How do I get y0 and x0 from this value? X0 is 3 and y0 is 0. So we get y minus 0 equal to root 3 is the gradient, m is the gradient, minus 3 is the x0. Alright, something like this. Okay, so we simplify this, we get y equal to root 3 in the bracket x minus 3. This is the first, what do we call? The equation of the tangent line. Alright, at 3, 0. Another one for case number 2, we have that dy over dx at t equal to negative root 3 is given by negative root 3. So this is the value of m at t equal to negative root 3. Therefore, we substitute inside the formula, right? Same procedure here. So this is the value of m, this is y0, this is x0. So we simplify this equation, we get y equal to negative root 3 in the bracket x minus 3. So now we obtain two equations of the tangents at 3, 0. Okay, let's now move to example 7. Suppose we have these parametric equations and we are asked to find the dy over dx and also the second derivative. Right. So to find dy over dx, we do have to find the dx over dt and also dy over dt in the first place. Therefore, we find dx over dt as this, and also we differentiate dy y with this, and we differentiate y, we obtain this one. Right, so now we can substitute inside the formula for dy over dx, where dy over dt is this one and dx over dt is this one. So we have this formula. Next, we want to find the second derivative, meaning to say that we want to find this using the formula. So for this part, meaning to say that we have to differentiate dy over dx again. So we have this dy over dx here. So we need to differentiate dy over dx with respect to t. Alright? We have to differentiate dy over dx with respect to t. So to do this, meaning to say that we have to differentiate this dy over dx. How do we differentiate this? We have to use the quotient rule. So to do the quotient rules, we have to determine the u is equal to 3t squared minus 2t and v is equal to 1 plus 2t. So we differentiate u, we obtain this, and we differentiate v, we obtain this value. So now we substitute inside the formula for the quotient rule. So this is the formula for the quotient rule. So we have to multiply this with this one. So we minus this one, multiply with this one. So we substitute inside the formula, we obtain this value. We have to simplify and we obtain this function. So now we already have this part, meaning to say that the one that we differentiate dy over dx with respect to t. So this is the value. So we put it inside here. So we put it here. For dx over dt, we take it from this one. So we have 1 plus 2t. Simplifying this, we get 6t squared plus 6t minus 2 over 1 minus plus 2t to the power of 3. Now, if the question asks, determine the equation of the tangent line at t equal to 1. So what we need to do is to find when the value of t is equal to 1, what is the values y, x and also y. So when t is equal to 1, we substitute the value of t with 1 here. So we have x equal to 2. And we substitute the value of 1 inside the y function there. We get y equal to 0. So in our mind now, x, y equal to 2, 0. So now, we already have, alright, because we know that the equation of the tangent line will need us to find the what do we call the gradient. So we already find the gradient using the previous slide just now. Dy over dx is given by this function. Alright, so but we want the gradient specifically when t equal to 1, so we have to substitute the value of t is equal to 1 inside dy over dx. So we have these, so simplifying this we'll get 1 over 3. So this 1 over 3 is actually the gradient, so denoted by m. We know that the tangent line is actually a straight line, so we can use the formula for the equation of the straight line, which is given by this formula. So we substitute the value of m with 1 over 3. What about y naught and also x naught? It comes from this one. So we substitute y equal to 0 and x naught here is equal to 2 and m equal to 1 over 3. Simplifying this equation, we got this equation of the tangent to the line at t equal to 1. Next, let's see the arc length. We have a theorem saying that if a curve C is described by the parametric equations x equal to ft, y equal to gt, for t is between c and d, in which f prime and g prime are continuous on the interval c and d, and c is traversed at least once when t increases from c to d. Therefore, the length of c is given by this formula. Let's see example. If the curve is described by these parametric equations, finds its length. Right, so firstly we find the dx over dt, which is given by cos t. Now we have to find dy over dt, which is given by negative sine t. Recall the formula for the arc length given by this formula. So we see that c is actually 0 and d is actually 2 pi. And this can be substituted with cos t and negative sine t. So we have these values. We substituted it. Alright, so we simplify this. We get this is actually from 0 to 2 pi. Alright, so that one is cos square t plus sine square t. What does it mean? By the identity, this is actually equal to 1. So square root 1 is 1, so integrate 1 dt. So integrate 1 dt, we get t. Alright, for 0 until 2 pi. So we have to find 2 pi minus 0, which is given by 2 pi. So right, so that's actually a circle and the length is actually 2 pi. Right, so the length is actually 2 pi. Okay, it starts at 0 1 and then it goes this way and it stops here. Right, so this is the length is actually 2 pi. Okay, now let's see this last example here. Suppose we have the curve described by the parametric equations. Find its length. So firstly, to find the length, we have to differentiate x with and y with respect to t. So we have dx over dt and dy over dt. Now we use the formula given by this, where c is actually 0 and d is actually 2 pi. So we substitute inside this formula, we have this. So we get 9 cos squared t plus sine squared t, and this is actually equal to 1. So we have square root 9, which is 3. So we integrate 3, so we get 3t from 0 to 2 pi, substitute with the value from 2 pi to 0, so we get 6 pi. What does it mean? It means that it starts for this circle, alright, the curve start from this, alright, it moves this way, 2 pi. So it move again 4 pi and it move again is actually 6 pi. Sorry for my drawing. Alright, so it's actually 6 pi. So the length is actually 6 pi. Alright, that's all. Thank you for watching.